Okay, welcome. So, last time we talked about the general equilibrium stuff. We went through the optimization, the way that the household wants to choose the capital flow, which thus sort of determines their consumption path, right? And you can work that problem out on your own. You'll kind of understand intuitively what's going on there a little bit more. But in the meantime, now that we've gone through that, let's learn a little bit more, right? Because there are going to be two kinds of equilibria here. There's like the equilibrium between the markets, and then there's kind of like the dynamic like stuff between time periods. Now, we got the first part in the last lecture, right? This lecture, we're going to be getting the second part, and it's what's known as a steady state. And this concept is going to give us an understanding of how these endogenous variables are evolving over time. And what we're going to do is we're going to force them to grow at the same rate. So everything becomes constant, which is then going to tell us how they behave when they're at rest. If we can understand how they behave when they're at rest, then we can kind of go, okay, let's shock this variable and see how it moves. It's one of those like, it'll spike up and then it'll kind of trend back down towards its original long run equilibrium, or it could converge to like a new long run equilibrium. So let's list off our equations. Well, I got equation 1, which is the Euler equation, right? Notice I fixed that error there. So you're going to want to go with this equation 1 when it comes to the Euler equation. I've got the resource constraint. I have the law of motion of capital. I've got the production function. And then I've got this equation that describes how technology evolves over time. Now, equation 5 isn't really going to be super important for us, so let's not worry about that one. I just kind of put it there just in the interest of, being complete because, I don't know, you just kind of get it drilled into your head over all the years. So let's get back to the steady states. We're going to start with the Euler equation. All right, so in the steady state, right, we're going to put a little SS subscript for everything instead of a T subscript, so CSS, which is steady state consumption. When we have steady state consumption, current and future consumption are the same. So, what did I do here? Well, with equation 6, right, look at equation 1. I got 1 over C, or 1 over CT equals beta times 1 over CT plus 1 times the marginal product of capital less depreciation. If I got 1 over CT equals beta times 1 over CT plus 1 times that other stuff, I can multiply both sides by CT plus 1. So now I'm going to end up with CT plus 1 over CT. And CT plus 1 over CT is equal to beta times the marginal product of capital less depreciation. So beta times the marginal product of capital less depreciation is equal to the growth rate of consumption. And in the steady state, if CT equals CT plus 1, then we're assuming the growth rate of consumption is constant. Now, we're also going to be assuming KT and KT plus 1 are equal to KSS, steady state capital. So capital will be constant over time as well, right? And then we're just going to sort of throw the same thing in for technology. So if I get the growth rate of consumption being constant, CSS over CSS, that's equal to 1. So if you got a constant growth rate, right, that's just 1. If you got, new over old and new equals old, 1, done. So 1 is now equal to beta times the marginal product of capital less depreciation. So I'm going to move beta over, and then I'm also going to switch out the 1 plus rho. So remember, beta is 1 over 1 plus rho. So if I get 1 over beta, that's just equal to 1 plus rho. So I get 1 plus rho equals the marginal product of capital less depreciation. Well, I got 1 plus stuff on each side. Okay, so I subtract 1 from each side, and I get rho plus delta equals the marginal product of capital. I also added delta to both sides. All right, so I want to isolate KSS, right, because I'm actually solving for steady state capital via the Euler equation. I know it seems kind of counterintuitive. You're like, would you be getting steady state consumption? You'd like to, but the thing is, remember, you've got CT and CT plus 1 in there. And so when those two guys are equal to each other, and it's 1 over CT, equals beta times 1 over CT plus 1, everything gets moved over. Well, that just completely cancels out. So we're going to use this to get steady state capital instead. So I get rho plus delta over alpha times A equals KSS to the alpha minus 1. Now I'm going to flip the numerator and the denominator on the left-hand side, and that means I'm going to be multiplying the exponent by negative 1. So instead of alpha minus 1, I get 1 minus alpha. Neat little trick there. So I get alpha times A over rho plus delta equals steady state consumption to the power of 1 minus alpha. All right. Now steady state capital is equal to alpha times A over rho plus delta to the power of 1 over 1 minus alpha. All right, if you need a little bit of review on your exponent rules, feel free to go through that. If you have questions, of course, you can always email me, and I'm happy to answer. So KSS, right, that's steady state capital, and it's a function of capital's share of income, technology, depreciation, and how impatient you are. Now, next, we're going to want to get steady state output. So what I'm going to do is I'm going to take the above equation for KSS, steady state capital. I'm going to plug that in for K in the output equation, which then gives me steady state output. So to get steady state output, I take steady state capital, plug it into K. All right, so if K is equal to this, and I've got the production function in the steady state in equation 8, I literally just take the right-hand side of what's all in pink there, and I plug that in for KSS, and that gives me that. And that's steady state output. So that one's easy. I got steady state capital, steady state output. Now I need steady state investment. So I take the investment equation, and I put SS subscripts on it, so I get this. ISS equals KSS minus 1 minus delta times KSS. Now, before I plug in steady state capital, we can clean this up. All right, if I distribute that KSS through the 1 minus delta, I get KSS minus KSS plus delta times KSS. Well, anything minus itself is 0, right? So I get steady state investment is equal to delta times steady state capital. Now, why is that? Let's think about that one for a second. If investment is the same, all we need to do is be putting enough capital, or all we need to be doing is to be putting enough capital in such that we are putting it in exactly at the rate it's falling apart, right? So it is exactly at replacement and nothing else. Because if it's anything else, well, things are growing, and that's not what we want. We want everything at rest. We want it constant. So now I can plug in steady state capital, and I get that. So steady state investment is just delta times KSS. If KSS is alpha times A over rho plus delta, all to the power of 1 over 1 minus alpha, well, there we go. We got that. Equation 10 is steady state investment. Now I finally can get steady state consumption. How do I do that? Well, I'm going to take the resource constraint, and since I already know steady state output and steady state investment, steady state consumption is just steady state output minus steady state investment. It's just a little bit of algebra here. I mean, I know it looks like a lot because there's like, a lot of like variables and stuff, but at the core, right, the basic like intuition of all of this stuff is just it's simple algebra. So what do? Well, I plug in steady state capital, steady state output. Boom, there we are. So this is steady state consumption. Now, we could go through and try to simplify some stuff. I'm really not interested in that. This is fine as it is. So now, why do we care about this stuff? Well, we care because we want the endogenous variables to be in the steady state so that they are unchanging over time. So we now have an equilibrium across the markets, but it's also an equilibrium in the concept of time. If they're constant over time, we can analyze what increasing or decreasing a certain variable is going to do to the entire system. So if we can see what happens to the time path for these variables, if one of the exogenous variables is changed, right, the only way we can really do that is to parse out the short run and the long run behavior. If you force it into long run behavior, you remove the short run behavior, right? Forcing it into long run behavior is forcing the steady states. And once it's in the steady state, then you can go, all right, let's change something, right? Because if you ever have an experiment, if you're doing an experiment, you don't want two moving parts at the same time. You only want one moving part. So here what we're doing is we're assuming that we've got multiple moving parts over multiple points in time. If we force everything into the long run rather than just looking at short and long run, we only look at the long run, and then we change something, we can see what's actually going to happen here. So if we change a parameter, or if we change one of the exogenous variables, right, we can see what's going to happen. So let's think about steady state capital. What happens to steady state capital if some of these variables increase? Right? What about alpha? Let's say alpha goes up, right? What is alpha again? Alpha is capital's share of income. So if alpha increases, right, let's just take a look at this. Okay, the answer is here. If alpha increases, it's also going to be increasing steady state capital. How do we know this? Well, first, it's in the numerator, right? And also, if you're to play with the exponent as well, right, just plug in some random numbers and see what happens to A, or alpha, I mean, not A. Now, what about A? Well, if A increases, steady state capital increases as well. Now, this one is a little bit more intuitive to try to explain out. Why? Well, think about it. If A increases, what does that mean? That tells us if we increase A, we are increasing the technology that's available for use in production in our economy. If Elon Musk invents, I don't know, let's say he's the inventor of warp drive, right? We all know it's Zephram Cochrane, but let's just assume for a second Elon Musk actually beats Zephram Cochrane to it. Maybe the annals of Star Trek just got everything horribly wrong with just the names. Everything else is correct, but the names were wrong. Okay, Elon Musk invents faster than light flight. Well, that is a major, major technological advancement. If we have that, right, we can produce more efficiently, meaning we can produce more with like the same amount of goods. Well, if we can produce more stuff, right, more is being produced, there is going to be more income. If there's more income, there are more resources available for consumption and investment. So if we're going to be increasing consumption and investment, we increase investment, namely, steady state capital is going to be increasing. Now, if you look, it's also in the numerator. So if you were to just increase something in the numerator, well, that just because fractions, that's going to be increasing steady state capital, right? But let's look at the two guys in the denominator, rho and delta, right? Rho is how impatient you are. If you're more impatient, you're less likely to invest, right? Because you want to consume more today and invest less. So if you're more impatient, well, you're consuming more, which means you're buying less capital. And because you're buying less capital, you're buying fewer investment goods, more consumer goods, then steady state capital is going to fall. And what happens if delta increases? Well, if the rate of depreciation increases, then steady state capital will also fall. Now, those two guys are in the denominator. So if you increase anything in the denominator, because fractions, right, the overall number is going to fall. All right, but let's go back to that A term. Let's say we were to increase our savings, right, which means that rho falls, or if depreciation falls. That's awesome, okay? That keeps us on the same growth curve. But what's cool about A is that increasing it is actually going to shift the growth curve. And it's one of the cool little things that I didn't tell you about when I showed you the firm's production function. I wanted to wait until we get to here, because then you can kind of see how it works and the way all these moving parts are operating. It's pretty cool stuff. So from this is steady state output, right? If we get an increase in A, then steady state output is going to increase dramatically. And then as a result, steady state consumption and steady state investment increase. Steady state investment increases as a result, steady state capital increases. So they all go up. So this is going to be an illustration of an increase in A. So I've got steady state output, steady state capital. Now let's assume I were to invest more. I just buy more capital, right? Well, if I increase the capital stock a little bit, well, steady state output, or just output really in general, isn't going to be increasing. by all that much. It does increase, right? But if you look at the amount that K increases by, that is a much larger amount than what Y increases by. However, if we have a technology shock, if there's a technological advancement, I didn't even change the capital stock, and look at what happened to output. Output increased dramatically. So you can produce more with the same amount of stuff with new technologies. All right, I mean, there have been these dire predictions for, God, hundreds of years at this point that the Earth's going to run out of resources and everybody's going to starve, right? There's the Malthusian argument about that. But, has that come true? No. Have really any of those predictions come true? No, they really haven't, because there's innovation. The more we innovate, right, the more stuff that we are producing, that we're making, the more ideas we're getting. Ideas are really what drive growth, right? Ideas, if I'm going to cite Deirdre McCloskey, ideas are like what changed the world here. We get a new idea that can be used in production, then we can use the same amount of capital goods and produce way more output. All right, so if you want to compare, if I increase the capital stock, but I'm on the same growth curve, okay, cool, you get a little bit of, a little bit more output. You're not really getting growth, though. You're just getting more output. Growth comes from that A term. But the steady state stuff in this particular context, right, looking at like changes to technology and all that, tends to be used in growth and development. It's also used for supply side shocks and business cycles. So there are a couple of different schools of thought when it comes to macroeconomic stuff with respect to business cycles. One of them is real business cycle theory. Now, it's not entirely wrong. It's also not entirely correct. They get some stuff right. They get some stuff wrong. Now, it's a school of thought that really says business cycles are driven by real factors, not nominal factors. Right? That A term, total factor productivity, is driving a real shock. Why is that? Well, it's affecting output. Right? It's affecting the productivity of our firm's production, right? If that increases, it's increasing Y, it's increasing output. Output is nominal, or not nominal, sorry, output is real, not nominal. So that total factor productivity term plays a really big role into getting us into and out of recessions. However, in the short run, there are both real and nominal variations that describe changes in economic variables. So if you want to look at things like changing the money supply, how that might affect economic output, and if it doesn't, why it doesn't, then you're really going to need to go beyond real business cycle theory. And that's like where the new Keynesian school of thought comes in, because what we just went through, right, there were no nominal variables here, right? These are all real variables. If you change a real variable, great. You're going to be changing, some other real variables. But if you're to change a nominal variable, on the other hand, then according to this particular model and classes of models like what we just went through, it's not going to change any real variables. But we've seen from previous lectures that if you change nominal variables, there are times where real economic variables respond, at least in the short run. They may not in the long run, but in the short run they do. So I'm not super concerned about playing with steady states for now. So what I'm going to do is I'm going to end it here. But to wrap up everything we've done so far, we endogenized output, we solved an optimization problem, found the general equilibrium, and we solved for the steady state equations, which then describe how these endogenous variables behave when they're at rest. Next, we're going to learn about general equilibrium, and we're going to be doing it with money, taxes, bonds, and a government. So we're going to be introducing nominal variables. Now, spoiler alert, it's still going to be a real business cycle model, right? It's going to be like basically, just an extension of the neoclassical growth model, only put in a business cycle context. It's driven by real factors, not nominal. So if you put in nominal variables, it's not going to be affecting any of the real economic variables, which isn't necessarily wrong. We just have to think about it in terms of medium to long run behavior rather than short to medium run behavior. So with that, I'm going to wrap up this lecture. Thank you for sitting through this one as well. and there's going to be more fun stuff to come in the future. Peace out.